Welcome everyone, and thanks for that nice introduction. I'm Erdem Bıyık. I'm an assistant professor at University of Southern California, and in my research, I work on human-robot interaction and multi-agent systems, such as a human and a robot collaborating on stacking a burger or building a structure together, or assistive settings such as an exoskeleton helping a person walk, or larger multi-agent settings where we have a number of autonomous cars interacting with a large number of human-driven cars. In all these domains, robots should first learn the behaviors of the humans or the other agents that they're interacting with. Because in that way they can increase the efficiency or for example, the comfort or the collaboration performance in these settings. For example, if they can anticipate the human actions, they can improve efficiency in human-robot collaboration, like the burger stacking or building structure tasks, or they can increase comfort or safety of an exoskeleton, or they can mitigate traffic congestion in a traffic network. So how can we make these robots learn the behavior of the humans or other agents that they're interacting with? And maybe machine learning is the answer. We just need to collect some large data sets and train a large model to learn these behaviors. For example, like we have seen this as a successful solution in many different domains. Like for instance, OpenAI trained GPT-4 using a lot of text. We don't even know how much. 1 petabyte is just an estimate that is usually discussed on the internet. Or there is ImageNet. It consists of 14 million images, and it led to human-level image recognition performance. AlphaZero played millions of chess games on its own and became a superhuman chess engine. So it seems this collecting large amounts of data idea just works. But what is the state in robotics? Today, the state of robot learning looks like this. This is a video from Google's ARM farm. A few robots are working nonstop to learn hand-eye coordination. And the problem is, compared to millions of chess games every day, this is almost nothing. And the problem gets even harder for human-robot interaction tasks because we need human models. We need to learn from humans. So in addition to the cost of robots, we need real people to sit in front of these robots and control them or interact with them. That's way too expensive. So in our group at USC, we develop robot learning algorithms that tap into different sources of information, especially from the humans. For example, we try to use humans' demonstrations, language instructions, gestures, gaze, etc. In my talk today, I will present 2 different projects that we conducted with this goal in mind. First, I'm going to talk about how learning from demonstrations is not very reliable and how learning from comparisons solves some of its problems. And next, I will present a new type of feedback based on learning from comparisons that humans can use to train robots using some language data as well. Okay, let's start with learning from comparisons. So in robotics, one very common way to learn objectives for robots is to collect some demonstrations from the agents the robot is interacting with and then learn a policy or a reward function for them. For example, behavioral cloning is one such idea that has been around for more than 35 years now. And in case you are not familiar with it, it just solves a regression problem. Given the state of the system, it predicts the action. So it learns a mapping from states to actions based on human demonstrations. And these learning from demonstration methods, they work great in many settings. For example, many works, including some of ours, use learning from demonstrations techniques to learn safe and efficient policies for autonomous driving. But these techniques are usually not sufficient for learning an optimal policy. For example, in our work shown in the middle, we had to learn multiple policies and try to optimally switch between them. So what's wrong with these methods? Why can't we just imitate the human and have a perfect driving policy? One of the reasons for this is human demonstrations are often suboptimal. To more concretely see why learning from demonstrations may fail, let's look at the problem mathematically. We are given a set of demonstrations, let's call this set D, and these psi variables are basically the robot trajectories. And there's a function phi that maps each trajectory to a set of features. For example, here's a robot trajectory where the goal is to reach the notebook on the table without colliding the obstacle. And here the features can be, for example, final distance to the goal, how close the robot gets to the obstacle, its average speed, etc. The assumption is that the robot is trying to optimize an objective, and this objective, the reward function we are trying to learn, is a parameterized function of these features. So essentially, what I'm trying to do is to learn these parameters W. One way of doing this is through an approach called Bayesian inverse reinforcement learning. In this method, we find the posterior distribution of the parameters vector W given the demonstrations. We can take its, like after we learn this posterior distribution, we can take its maximizer, or we can take its expectation as our learned reward function. Or we can even use it as a distribution if we need to model uncertainties. So how do we do this? Well, we use Bayes rule. Here, the first term is just the prior. And for that, we can use a uniform distribution, or we can incorporate some domain knowledge if we have it. But the important term here is the second term, the likelihood term, because it will add the information from demonstrations into the model. For that, in Bayesian inverse reinforcement learning, first, we assume the demonstrations are conditionally independent. Like given the reward function, the user's demonstration to the robot does not depend on their earlier demonstrations. And this is usually an okay assumption. And we also assume the likelihood of demonstrations comes from a noisily optimal human model, the softmax rule in this case. And this final expression here, or maybe like, let me elaborate a little bit on this model. So what this says is that the probability of a human demonstration is proportional to the exponential of the reward of that trajectory. So if a trajectory is better in terms of the reward, the human is more likely to give that as a demonstration. So it's very intuitive. But the problem here is that this noisily optimal assumption, like even though it's intuitive, it doesn't hold in practice. Like even though this human model, this softmax model that I was talking about, it tries to capture the human suboptimality, it asserts that the optimal trajectory is the most likely demonstration. But for example, the trajectory that I'm showing here in the picture, it's the optimal one, but it's definitely not the most likely one, because humans will not be able to teleoperate the robot to move as smooth as this. In fact, this robot is just too difficult to control. Here you are seeing my former lab mate, Andy, and Andy has a lot of experience with this robot. He's trying to teleoperate it to perform this task, but he's having a hard time because this robot has 7 degrees of freedom. So it's really hard to teleoperate it. Also, the problem is not specific to teleoperation. In fact, humans are far from being optimal decision makers. There's a work from Berkeley where they showed humans do not like their own driving. They think it's too aggressive. And after that, we showed humans are consistently making suboptimal decisions when they encounter situations that involve risk. And if we are not able to give good demonstrations, then how can we even hope to learn from these demonstrations? So we need a better way of learning objectives. One idea is to have the robot itself demonstrate a trajectory to the human, and then the human will assess how good, how successful this trajectory is. However, this is also not an easy task for the humans. They often provide unreliable data, and it may not be obvious why. So for this, when I give similar talks in person, I usually ask this seemingly unrelated question. And the question is, how dark is this blue? And people often say things like a little bit, or it's not that dark, etc. But when someone says a little dark, that's very ambiguous. And in fact, we humans are not very good at making these kind of assessments or giving ratings. So if I ask a user how good a robot trajectory is, they may say things like, that's kind of good, and it's very ambiguous for me. Instead, humans are better at comparing things. So instead of asking how dark is this blue, let's say I introduce a second color and ask which blue is darker. Now everyone will give the same response to this question. It's very reliable. And we actually generate comparison data all the time. Like every time we make a selection in Uber or Lyft, or every time we click on a YouTube recommendation, it's a preference over the other options. Similarly, our actions generate comparison data. Google Maps gives us multiple navigation options, and we take one of them. Google then understands we prefer that route over the other options. So we implicitly make a comparison. And our idea is to have robots leverage such comparative data to learn the objectives of humans accurately. So in this first section of the talk, I focus on how we learn from comparisons. Okay, what is comparison data in robotics? First, the robot shows two trajectories to the user, and then we ask the user whether she prefers trajectory A or trajectory B. Her response gives us information about her underlying reward function. And if we go back to the Bayesian inverse reinforcement learning from a few slides ago and add the comparison data into the framework, this is what it looks like. So in this new setup, we will have a second data set for comparisons, where each data point is a tuple that consists of two trajectories, A and B, and the user response. So Xi A and Xi B are the two trajectories, and Q is a binary choice of the user between these two options. So how does this new data set affect our posterior? Well, first, we are now given two data sets, demonstrations and comparisons. We first factor out the likelihood of the comparison data set. So we assume these two data sets are conditionally independent. If I already know the conditionally independent in the sense that it's conditionally independent, conditioned on the reward function. So if I already know the reward function, then comparisons and demonstrations do not depend on each other. Right? And similarly, we expand the likelihood of each user response. So comparisons are also conditionally independent from each other. And in the final step, we again make the noisily optimal assumption. So the way I'm writing it here is not exactly accurate, but it's like proportional to this in a sense. But if you want the full formulation, it would look like on the numerator, we would have the reward of one trajectory inside of an exponential, of course. And then in the denominator, it would be the two trajectories. Right? So we are really, again, making the same assumption of noisily optimal human decisions. But importantly, this assumption doesn't hurt us here because it's not the humans who teleoperate the robot anymore. The robot is generating its own trajectories, and then the human user is just choosing which of them they prefer. At the end, we have this unnormalized posterior, and by maximizing it with respect to W or taking its expectation, we get a good estimate of the human's reward function. When we implement this optimization and when we solve it with human data, we were able to check how well the robot achieves the task when it learns the objective using both demonstrations and comparisons. Here, the data collected for two different algorithms had the same convergence rate in simulations. So in the Bayesian IRL one, we have several demonstrations, and for ours, we have one demonstration plus some comparison data. As you can see, the Bayesian IRL robot tries really hard to avoid the obstacle, but fails to achieve the actual task and gets stuck in a weird configuration. On the other hand, the robot trained with comparisons eventually reached the goal while also not hitting the obstacle. So overall, the point is that robots can learn from comparisons in addition to demonstrations. And in fact, they should, because we have a huge data problem in robotics. So we should make our robots learn from every possible source of information. And luckily, humans are better at comparing trajectories than giving demonstrations to the complex robots. And it's great that we can learn from these various data sets like demonstrations and comparisons. But even if we were to use these more reliable and expressive sources of information, we still haven't solved the data problem. We simply do not have large data sets, let it be demonstrations or comparisons, especially like in robotics applications. So instead of blindly collecting large data sets, we should have more intelligent approach that optimize what data we should be collecting. For example, we should try to find the most useful comparison queries. And one thing is very important to note in our learning problem. In the case of demonstrations, we have had a user giving demonstrations to the robot. We had control over nothing. It's the user who decides the entire trajectory. On the other hand, in comparisons, we again have the robot and the user, but now the robot first shows some trajectories to the user, and then the user responds. We again have no control over the user's response, but we do have control over what trajectories to show. So we can actually find an intelligent way of choosing those trajectories to, for example, accelerate the learning of the objective. To do this, we formulated the active querying problem with an information theoretic objective that not only considers the robot uncertainty, but also models the human uncertainty in responding to queries. So what we do is we maximize the mutual information between the user's response and the belief about the reward function, given the data sets that are collected up until that point, and the queries that we are going to make. And again, when we implement these methods significantly outperform the state-of-the-art method at that time. And in our simulations, we were able to learn the user's objectives within as few as 30 queries as opposed to 100, like 100 of the previous results, I mean. So overall, like in this first section, we have seen how active preference-based learning can help us better learn models of human behaviors, rewards, or policies. Besides the works I mentioned so far, I've been working on a number of other directions in the space of active learning and reinforcement learning from human feedback. Unfortunately, I don't have time to talk about them in detail today, but I'm happy to discuss any of these directions offline. Let me briefly mention 3 core categories that I've been working on. First, like we developed richer forms of comparative feedback, such as scale feedback, using a slider which enables users to indicate how much they prefer one option over the other. And these richer forms enabled us to learn more general reward functions in a data-efficient way. We also looked at how we can use the comparative data, such as latency and price trade-off in Uber and Lyft, to reduce traffic congestion through pricing strategies. Finally, we developed active preference-based Gaussian process regression techniques that go beyond simplistic reward assumptions such as linearity and applied them to exoskeleton gait optimization. Here, the patients cannot possibly give demonstrations. Besides, testing is very demanding for them, so data is really, really expensive. Our active learning approach that used comparisons enabled us to quickly learn their preferences. Overall, the key takeaway is that comparative feedback can be actively collected, and if we are trying to learn as quickly as possible, then the robot should ask questions that it doesn't know the answer, but the human user does. Okay, so this is all great. However, comparisons have their own drawbacks too. For example, they simply take too long in many applications. If I want to give a feedback to this robot with these preference comparisons, I need to watch the robot do the task once, then somebody should reset it, and then I will watch it again. At the end, I'll give my preference, and guess what? It's at most 1 bit of information, even though it was actively generated. Right? So I'm giving the system very little information, even though I spent a lot of time on this. Or like take ChatGPT. If I'm lazy enough to ask ChatGPT to write my emails, am I really going to read these 2 long responses to my prompt and select which one I prefer? And it's not just the time it takes. Binary comparisons do not really tell us any information about why we prefer what we prefer. Let's take these 2 robot trajectories, for example. Here, the goal is to reach the ball without hitting the blue obstacle on the side. So when the robot asks me which trajectory I prefer, I'll choose the second one. But does the robot know I chose it because it gets closer to the ball? Not really. It could think Erdem wants to reach the obstacle, or it may think Erdem prefers the arm to move closer to the ground. So instead of binary comparisons, wouldn't it be nice or more natural if I could just say, I want you to move closer to the ball? So in the second section of the talk, I'll talk about how we learn from comparative language feedback. Okay, what is comparative language feedback? It's simple. The system will now demonstrate a single trajectory to the human, and the human will give comparative feedback using language. So in this case, maybe he will say, move closer to the cube. The challenge is that when the user says move closer to the cube, the robot needs to know what it means. In other words, the robot needs to know the grounding between its own actions or trajectories and humans' language. For this, our idea is to learn a shared latent space. You can think of it as the latent space in machine translation. Instead of trying to map sentences from English, Turkish, Vietnamese to the same latent space, we will try to map comparative language and trajectories into the same space. To do this, we will collect some comparison dataset. This is all offline pre-training, so we will do this only once, not every time we need to learn the preference of any user. The samples in this dataset consist of 2 trajectories and a human annotation about how they are different. For example, the annotation may say trajectory B moves faster than trajectory A. Importantly, this is not a preference between the 2 trajectories. The human will just state what one difference between the alternatives is. They do not need to tell us which one they prefer. Of course, there are many ways to say trajectory B is faster than trajectory A, and we want to be able to understand all of them. So what we do is we use large language models to augment our dataset. If the user says trajectory B moves faster, the language model will augment it with trajectory B moves more quickly or trajectory A moves slower, etc. After we create this dataset, we use a pre-trained encoder like T5 to encode the human's language feedback. We could also try to train our own encoder, but that would require too much data, so we just use a pre-trained model. We then embed each trajectory with an encoder. Now, this is where we have to align the language utterance with the trajectories. We know that this language utterance, trajectory B moves faster than trajectory A, describes trajectory B relative to trajectory A. So what we do is we create a loss function that tries to match the embedding of the utterance with the embedding difference of the trajectories. With this loss function, we train the trajectory encoders and finally fine-tune the T5 model. After training, we checked if our latent space can accurately predict whether two trajectories satisfy a given language utterance, and the results seem quite promising. Okay, so we have this latent space now. In this latent space, each trajectory corresponds to a point, and each comparative language utterance is a vector. How do we use this? There are many different ways we can use it. Let me give you two examples. First, we can iteratively improve trajectories. So let's say the robot starts with an initial trajectory 0. The user says move slower. We know what vector it corresponds to, so we can go in that direction and find the trajectory there. We again show it to the user. Now the user gives another feedback, maybe says move closer to the bottle, and we do that to find the next trajectory. The robot asks again, and so on. When we implement this, we saw we can get consistent improvements with this comparative language feedback. You will notice, though, it doesn't reach to an optimal trajectory. It's because this improvement model is memoryless. It only updates the most recent trajectory with the most recent feedback. So it may sometimes get stuck in loops between trajectories. But there's another way to use the latent space, which is a learning-based way, more like reinforcement learning from human feedback, if you like. We again start with some initial trajectory. The user gives some feedback. Let's say they said move lower. Again, we know what it means in the latent space, but now we don't try to find the trajectory at that point. Instead, we say the trajectory at that point is preferred over the original trajectory, and we can add it to our data set as if it is standard comparison data. So just by showing one trajectory and asking for feedback in plain language, we can synthesize the preference comparison. But that's not the end of the story. There is more information we can use in this move lower feedback. That's because the user intentionally chose to say move lower. They could have said move faster or move farther away from the bottle, but no, they chose to say move lower. This means they likely thought this feedback has the highest potential to improve the trajectory. Mathematically, this is equivalent to saying this improved imaginary trajectory after the move lower feedback is better than the trajectories that would be the result of other language feedbacks. So we can find these alternative trajectories from other language utterance that didn't happen and add such comparisons in our dataset. So we are really using this one comparative language feedback to create many implicit preferences as opposed to just one. We tested this on 2 robot simulators and saw that if you use both the implicit and the explicit feedback, you get much higher data efficiency. We also compared this language feedback to standard preference comparisons. Language feedback has been at least as good as preference comparisons in learning the reward functions, if not better. Finally, we did some human subject studies to test the framework with a real robot. Our user pool is not super large. We only had 10 users, but it seems there is some tendency to prefer giving language feedback to the robot instead of preference comparisons. And we also recorded the time it took for the users to give feedback. You can see that language feedback is a little faster. And this doesn't really give the full picture because here the users gave the language feedback by typing what they want to say. If we had a speech to text interface instead, the language feedback would be even faster than this. So today I'm saying preference comparisons are also inefficient. Let's try to use comparative language to get feedback from humans. And it's not just a robotics thing. It might be even easier to do in other domains. For example, take language models. You could probably sidestep the data collection for pre-training because you don't need a human annotator to tell this text is less technical than the others. You can easily create millions of such data yourself. You will just give a text to the language model and say, make it less technical. It will do it for you. And now you have a data sample that you can use for pre-training. So we have seen how comparative language feedback can enable humans to train robots in a way that doesn't suffer from the suboptimalities of demonstrations, and also is more time efficient than standard preference comparisons. In addition to this, as I said in my lab, we are interested in learning from all sorts of human feedback. These include like interventions, gestures like hand gestures or facial expressions, or sometimes we even replace the human feedback with AI feedback, because now we have these large pre-trained models like large language models or vision language models that can kind of imitate humans very successfully in different domains. So sometimes we can even ask these AI models for feedback to the robots. And to end my talk, of course, I want to thank my students who carried out these works. Specifically, Zhaojing and Miru led the project on learning from comparative language, and we had collaborators that worked on the two projects that I mentioned today. With that, I can take questions.
I always like to come in the last minute.
Okay.
Let's take at least one. How do you decide whether it's worth collecting more human feedback from a cost perspective versus performance?
Yeah, so that's a good question. We have some results about it. So I briefly mentioned the active learning idea, where like we were deciding which query to ask based on some mutual information optimization. And that optimization is useful because it tells us how much information we can expect from a query. Now, the decision of whether we should continue collecting data or whether we should stop, it is like that mutual information metric gives us like quantity that helps us decide that. So in a sense, it's like initially it will start around 1 bit because these are just binary comparisons, and usually it will decrease over time because as we learn more and more, the uncertainty will decrease, right? So usually we stop when the information gain goes below some threshold. But that threshold decides how much we care about making the robot real precise versus a little coarse but with less human feedback. But that threshold is the only scalar that needs to be designed by the designers.